Hello everyone and welcome to the Vol 2 presentation. My name is Mike Ta.
I'm Vinnie Vu, and we're going to talk about the Vol 2 processor. Now, before we start, do we have any questions? Come on, Mike, put your hand up. We don't have time for this.
Alright, so here's the layout of our presentation. First we're going to talk about the origins of Vol 2, and then we're going to talk about the processor overview, the enhancements, Vol 2 Process 6.0, and Q&A. Now, how do we get the name? Well, as you know, Vinnie Vu's last name is VU, my last name is T.A. Ta. We combine our last names, swap the vowels. That's how we got the Vol 2.
And here at Vol 2 Industries, we have our famous motto, make Verilog great again. Just kidding.
What Vinnie meant to say is our motto is perfection is never ending. Alright, so here's the processor overview. First we're going to talk about the memory structure, the processor register set. Then we're going to look at the addressing modes, the instruction types and formats with examples, and then the diagrams. So here we are, the memory structure.
So here in our memory structure, we are using Harvard memory architecture, which means the instruction memory and data memory are separate. Now, since they're separate, I should let you guys know, or we should let you know that they are byte addressable and they're using Big Indian, shown here in this picture. And we are using 32-bit address space.
So now let's look at the processor register set. As our design, we have a 32-bit registers in register file, instruction memory, data memory, and I/O memory. Our program counter is 32-bit, plus a 5-bit flags register that include interrupt, carry, overflow, negative, and 0. And for the addressing modes, we have 3, immediate, register, and register indirect, which is only for store word and load word. So let's look at immediate mode. First, we have the immediate mode is either 16-bit I-type or 26-bit J-type immediate field. And the example we have right here is 16-bit field add immediate.
So here with add immediate, we're getting the contents of register S, which is register 3. We're going to add it with the immediate value 3. And the result of that will go into the destination register RT and register 4.
Now, to further illustrate what Vinnie said about the immediate mode, we're going to have another example of 26-bit immediate jump.
So with jump, I'm going to take the 26 immediate jump address hex value 69, and I'm going to put that into the program counter. So the program counter will go to instruction memory location 69 and execute instructions from there.
You actually wouldn't go to 69, correct? Because you'd be concatenating 2 zeros onto that 69 and so end up at a complete...
Oh yeah, 69, 0, 0.
Yeah.
Right.
So now let's look at the register mode. The values are stored in registers become manipulated using operations and are stored in a destination register. An example we have right here is subtract.
So subtract, I'm going to take the value from the source register RS, which is in register 2, subtract it with the second source register, register T, which is register 1. And the difference of that will go into the destination register RD, which is register 3.
Now let's look at register indirect mode. Well, in this mode, the value of the register is an address, location, and memory that we can use to either store another value in memory or read the destination register. The example we have right here is load word.
So load word, again, we are getting the value from register S, which is in register 5, added with the immediate value 0, go to that memory location, and then we get that value from the that memory location and then store it into the destination RT, which is register 10.
Is the immediate value signed or unsigned?
Signed.
Signed. Okay.
Now let's look at the instruction types. We're going to discuss 3 types: R-type, I-type, and J-type. And for the R-type instructions, these instructions use register addressing mode. Example we have right here is shift left logical.
Shift left logical, we are getting the contents of the source register RT, which is register 1. So let's assume register 1 has this value this hex value 10. We're going to shift it to the left once based on this shift amount. So hex value 10 now becomes hex value 20, and we will place this hex value 20 into register 1, which is also the destination register shown here.
Next, the ITAP instructions. Well, these instructions use the immediate addressing mode except the load word and store word, because in the load word and store word, they use the indirect addressing mode. The example we have right here is branch if equal.
So with branch if equal, we are comparing the two source registers RS and RT. In this case, they are registers 2 and 3. If they are equal, which they are, since register 2 has its hex value 100 and register 3 also has its hex value 100, the 0 flag will pop up, and then the program counter, which has this hex value 100, will be added, will have PC 100 plus 4, which is 1 of 4, and then plus the immediate value, which we have here as 4. So 100 plus 4 is 108.
And finally, we're going to look at the JTAP instructions. These instructions also use the immediate addressing mode, the 26-bit immediate one, and the example we have right here is jump and link.
So with jump and link, let us assume that the instruction is jump and link 440. So let us assume that the program counter currently has the value 301 before the jump and link. So what we will do is that we will store that program counter value 301 into the return address, register 31, and then the program counter will have this 26-bit jump address 440, and also with those 2 zeros at the end.
So it really would not be 440.
No, typo.
And then, can the program counter actually have 301?
No, that was just a reference.
True or false? Your boundaries for instructions have to be 4-byte boundaries? In other words, all references for instructions have to be a multiple of 4 bytes?
Yes,
Is that true? Is that true?
Yeah, true.
So it could never be 301 or 302 or 303?
No.
Great
It's
courses
just
though,
use-
great courses. I see what you're trying to do then.
Why, thank you.
Alright, let's look at the diagrams in the following order. First, we're going to talk about the top level. Then following that is going to be the CPU. Then control unit. After the control unit, it's going to be instruction unit. And finally, the data path. So we are at the top level. 3 important blocks. We got the CPU, central processing unit, the data memory, and the I/O memory. As for the signals, we have the data memory chip select, data memory read, data memory write. That goes into the data memory. The D out of the data memory will go into the DY as a 32-bit. The output of the CPU ALU out will go into the address, as well as the D out will go into the D in of the data memory.
Now, since Mike has talked about the data memory, let's talk about the I/O memory. So over here, the central processing unit will send its control signals, I/O strip select, I/O read, and I/O write to the I/O memory itself. And then, of course, the I/O out will give its 32-bit input to the I/O. 32-bit output to the I/O in. And of course, the I/O memory has the option of interrupts. So I/O memory can send an interrupt request to the central processing unit, and then once that interrupt is complete, the CPU will send the interrupt acknowledged into I/O memory.
Why is there a separate bus for I/O data going into the CPU?
We did not implement tri-state.
Hmm?
We did not implement tri-state.
Are you sure you didn't implement tri-state but just created another port? I mean, why did you create that port, ION? It could come in on the DY bus. So why did you do that? What was your logic?
Easier access
At what cost?
at the cost of another 32-bit bus.
And you really felt that was worth it?
Now I think about it, no.
Because I think if I looked into those modules, the Verilog, I think you did implement tri-state on both those modules. So you need to take advantage of that.
Good.
Yeah.
Now let's look at the CPU. Similar to the top level, it has 3 important blocks. you got the control unit, the instruction unit, and the data path. As for the signals, I'm gonna go ahead and talk from left to right. At the top, you got the interrupter coming in from the I/O, and then once it gets a request, it's gonna send back the interrupt acknowledgement to the I/O. The data memory chip select, data memory write, data memory read, that goes into the data memory. And the I/O chip select, I/O write, and I/O read, that goes into the I/O memory. As far as all the flags, the carry, 0, negative, and the overflow, that gets it from the data path. For the high-low load, basically it's for the multiplication division. That goes into the high-low load of the data path.
Mm-hmm.
And all the present state flags of overflow, 0, negative, carry, and interrupt, that goes into the flags in of the data path.
So
What,
let's
can we stop right there? The present state of the flags go into the data path?
Yes.
Why?
In the event of an interrupt, we must save the flags into the data memory.
So the data memory is in the data path?
No, it's going to be going out via D out.
Okay, so you passed it through.
Yes.
Okay, thanks.
So now that we've discussed all these little parts, let's talk about how it's used in the instruction unit. So of course, the control unit will send its control signals to the instruction unit, such as PC select, PC load, PC increment, and IR load.
Mm-hmm.
and later on, the instruction unit will send this IR out to the control unit for the control unit to decode and send signals to the data path. While we're on that subject, that control unit will send these signals to the data path, like D enable, S select, D select, and T select. And later on, in the event of a return from interrupt, the ALU out from the data path will go into the flags of the control unit. And of course, we should not, let's not forget about these output. The D out goes into the data memory. DY, that's the output of the data memory, and then IO in is the output from the IO memory.
And data out also goes to I/O memory?
Yes,
So there you have one shared bus going to both.
right.
So in the reverse, that's why you have one bus going to both.
Oh, yeah, right.
When we fix that.
Okay. So to look closely into the control unit, we spoke a little bit about the signals. So as you look at it, the interrupt comes in from the I/O, the CZ and V coming in from the data path, and the instruction register coming in from the instruction register. The 32-bit flags that came in as an input, and all this I/O, chip select, I/O read, I/O write, and that come in from that controls the I/O memory, and the data memory, chip select, data memory read, and data memory write, that controls the data memory.
So let's go from bottom right all the way to the left side. So here we have again the control signals for the data path, the enable, S select, hello, load, and deselect. And over here we have the control signals for the instruction memory, PC load, PC inc, PC select, IR load. And over here on the left we have our present state flags, interrupts, carry, negative, overflow, and Z, 0. They go to the data path as flags in. Oh, yeah. And of course, after completing an interrupt service routine, we're going to send interrupt acknowledge to the I/O memory.
Before you leave this one, flags up in the, why is that 32 bits?
Well, the flags input from the data path is as ALU out. Basically, that's a 32-bit flags to match the 32-bit ALU out. So as for the flags located at the least significant bit, the 5 least.
So that's the same five flags that are going out,
Yes,
but here it's 32 bits and here it's 5 bits.
right.
Okay.
Yeah. And for the instruction unit, we didn't change much of it.
So let's move on.
Ha! Now that looks sexy, Vinny.
Oh yeah, we were really intimate with that data path. Eiffel Tower. Okay, that was good. All right, so this. Okay, the data from the ALU out will go into the register file, but where it will go will be based on the deselect here in the demux. It's either 1D, stack pointer, 1F, return address, T address, or D address. Of course, here the S address and the T address will come from the II, from the instruction unit. And so let's go. Let's look at how the data goes from S to the ALU. So this output from the register file S will be going through an SMUX, and the output of that SMUX will be determined by SSelect, which will either select this output from the register file or 32-3FC. And after going through that output, it will go through the register RS, and then afterwards to the ALU. Now that we're talking about the S, let's talk about the T side. So here we have the T output going through the TMUX, and here the output of that TMUX will be determined by T-select. So we'll either choose the output of the register file here, or we'll choose DT, or we'll choose flags in. And then after going through that MUX, it'll be going through register T, and then it will go through the ALU. Of course, let's not forget that DL gets the contents of register T in the case of stores.
It's going to select which input it wants, and then it's going to go out to the LU out for the 2-bit. Now, for our enhancements, the baseline we have is the input, output, and the return from interrupt. The 3 that we made is the move, clear, and all else. Now, let's look at the input first. It's very similar to a load word, but instead of reading from data memory, it reads from the I/O memory. And the example we have right here is the input R1, 0, R2.
So here with this example, let us assume R2 has that hex value 1000. It'll be added with the immediate value 0, so 1000 plus 0 is 1000. We will go into that I/O memory location 1000. We're going to grab that. The contents from there and then place it into R1. So therefore, register 1 has this value AAAA5555.
Now, how do we implement this? In part 1, basically what we're doing here is the control word, and the ALU out gets RS plus DT.
In part 2, the I/O input in the data path gets the contents of the I/O memory based on ALU out.
And then in part 3, the RT gets I/O. Now let's look at the output. Very similar to store word, except the value is stored in I/O memory instead of data memory. The example we have right here is output R0, 4, R1.
So again, let us assume register R1 has a hex value 1000. So we will add it with the immediate value 4. So now it's 1004. We will go to that location in I/O memory 1004 and then load the contents of R0. So let us assume that register 0 has this hex value 42. So now this memory location 1004 will have the value 42.
And again, how did we implement this output? In part 1, ALU out gets RS plus DT, very similar to the input.
Okay. But instead of part 2, the I/O memory location based on ALU out will now get the contents of register T.
Following that, this is how the input and output in action, here we go. First, we load 100, 100 C0 into register 16. Then we initialize register 17 with 8000 FFFF.
So our first instruction after these load is output 17016. So what it means is that we're going to store the value of R17 into memory location specified by register 16. So you can see here in the results, I/O memory address location C0 will contain the contents of register 17, 8000 FFFF. And in the second instruction, we have input register $19, 0, register 16. What that means is that the contents of the I/O memory specified by register 16 will be inputted into register 19. So here in the results, register address 19, which is 13 in hex, will get the contents of memory location specified by register 16, which is 8000 FFFF.
What's the opcode for the output instruction?
I want to say 20.
So where in those 4 bytes?
Oh, right.
For the output instruction?
7.6, that is,
So did it have its separate opcode, or was it keyed to the E key, or what?
we did not put in the E key.
So
Alright.
you don't have an answer for that?
We did not have it in the E key, so it's just part of the,
So where did the opcode come from?
We assign an opcode to that. And
That-
You did? You assigned an opcode?
yes,
From where did you select that opcode?
from the instructions that we tested.
Okay.
All right, now let's look at the return from interrupt. Basically, this instruction put the save program counter value in the stack pointer register R29 back to the program counter.
Mm-hmm.
It also put the save flags values in data memory back to the present state flags located on at least 5 significant bits. And this is how the RTL looks like.
We will explain more of this RTL as we go through the code.
So are you pushing something there? You're or popping?
Popping.
So where did you adjust the stack pointer by 4?
We did not.
Then how could you do a pop? You can't just put 3FC in the stack pointer.
We did.
Okay, so walk through those steps again. Tell us what you're doing there.
Sure. Go ahead.
Oh,
Like that?
R29 goes to RS?
Right.
No, just go through those RTL steps, those 6 steps, and explain your logic, what you're doing.
all right, so, so the first step, we have register 29, which is a stack pointer. The contents of that will be loaded into RS.
Yeah?
In the second step, the register S, that has that contents, will be given to ALU out.
Okay.
And the third step, that ALU out contents will be given to the program counter. So now the program counter is restored from that stack pointer.
The stack pointer references memory. It's not a return address location. I'm a little bit confused here. And what
I saved that
the
program.
return address doesn't go into the stack pointer. Stack pointer is pointing to memory where you're supposed to save the thing.
Maybe it's a typo, maybe you wanted to load R31 into RS instead of the 29.
Not sure.
I saved the program counter in the stack pointer register. So
Yeah, that's a misunderstanding. You're supposed to save it on the stack itself, which is data memory.
but in
The stack
data
pointer
memory.
points to the place to save it. Then you're supposed to
Oh, okay.
adjust the stack pointer.
Oh, oops.
Okay, yeah, so you'd have to clean that up quite a bit.
Right.
Right. And then here we have, and then since we got the PC restored, we need to start working on getting the flags restored. So register RS will get this 32, this value 32 hex 3FC. Again, the ALU out will get our register S. Now we go to data memory, grab the flags from this value stored by ALU out. That goes to DY, and then DY, and then after that, the DY goes into the flags in the control unit.
All right, so the return interrupt, the part 1, we basically said that ALU out gets RS.
Part 2, here we have the restoration of the program counter, ALU out gets QC. So let's start working on the flags. 3253FC goes to register RS.
In part 3, the ALU out gets RS.
Part 4, here we have the DY in data path getting the value in data memory based on ALU out.
And then in part 5, the flags get updated. The flags get ALU out, which is DY.
And here in the bottom, we see the next state getting the values from the flags input in the control unit. And on the next clock tick, these values in the next state flags will be pushed on, will be into the present state flags.
And now for the move instruction, basically moves contents from one register to another. The example we have right here is move R2, comma R1.
So R1, let's assume it has that hex value 1000. After moving it, now register 2 has that value 1000 as well.
Did you create a new opcode for move? What's the opcode for move?
Opcode, we did not use the, I forgot to use, we did not use the E key, so the opcode will be 0, and the function is 30, hex 30.
And 30 isn't used by the MIPS for some other R-type instruction?
No.
You're sure?
Well, not that I know of, so.
So you didn't look, in other words? Because if you say, not that I know of, means I
Okay,
didn't
I didn't
do
look.
any research. Yeah,
Didn't
you
look.
can't do that. Similar. So for all of the, I don't know if it's, everybody said, yeah, that's what you're supposed to do, and we all just did the wrong thing, but these are big mistakes. These are major mistakes.
Right.
We're making a MIPS processor, so I can't overwrite current MIPS implementation. It's 2016, it's going to be 2017. There's a lot of the R-type instructions that you're just overwriting. So your whole decode logic is going to have to change.
Right.
Yeah.
Okay.
And then on the move, couldn't I, or like, let's take the clear, couldn't I just say, subtract R2, comma R2, comma R2? Why do I need a new instruction?
More simplicity.
But you have to, I can clear any register I want with a subtract or an exclusive OR. Why do I need a new instruction I have to pay? I'm the customer, now you're making me pay with power and
Right.
resources for something that I can already do with reduced instruction set computing. Like I can do a move by just adding R0 with register 0 and putting it into any register.
Okay, right.
It's a little bit wasteful, which is kind of going away from the idea why we do a RISC processor.
Right, I understood.
Okay.
Okay.
So we're good with the clear. Basic clear the contents of the destination register. The register gets all zeros.
And then here's an example, R2 has that hex value 1000, and then after active instruction, register 2 now has zeros.
And last but not least, the all Fs. Instead of putting all zeros into the destination register, it puts ones into the destination register. So here, the example we have here is all F, R2.
So again, let's assume that the R2 has that current hex value 1000. Have that all F's instruction, R2 want to have that hex value all F's. Or F.
Now, coming soon, there's going to be a Vault processor 2.0, and this is what we're going to do in the future.
We love working on this processor, and I say so much. We already thought about what we're gonna do next time. Turns us on. So this is what we will include: the barrel shifter, vectors, and floating points.
And of course, that concludes our presentation. Any questions?
Questions? I guess not. Thank you.